Welcome to Study Loop.
Okay. So we're trying to figure out the ratio of equatorial to axial cyclohexanamine. So really this is like a ring flip thing, right? We're saying we've got some equilibrium set up where in one case we've got this amine axial, and in the other case we've got an equatorial. And this has some equilibrium constant associated with this transformation. And, that is like saying K equals, if we call this equatorial and we call this axial, right? Equatorial is our product and axial is our reactant, right? We want the ratio of equatorial, concentration of equatorial to axial, right? That's what we're interested in. That's like an equilibrium constant, right? Products over reactants. They have told us that we're doing this at 20 degrees C, which is equivalent to 293.15 Kelvin. Okay. And they've told us delta G naught, right? They've told us delta G naught for axial to equatorial. We've got this in the correct direction, right? So this is the delta G naught that corresponds to K being equatorial over axial, right? Because our reactant is axial, our product is equatorial. Okay, so this is going in the right direction. Delta G naught is negative 5.9 kilojoules per mole. And that makes sense that energy would be released, right? Axial is higher energy than equatorial. So if our delta G is negative, that corresponds to our, intuition about going from a high energy to a lower energy state, that energy should be released. Okay, so how do we find K, right, given delta G? Well, they're related. If you recall, delta G naught equals negative RT ln K. That's the natural log of the equilibrium constant. That's the current temperature, and that's the gas constant. They told us the gas constant is 8.314 times, just 8, this is joules per mole per Kelvin. Okay, great. So we need to solve for K, right? And we just divide RT over, negative RT over, negative RT, negative RT, right? So we get delta G naught over, let's move the negative to the top, just out of convenience, equals ln K. How do we get something out of a natural log? We exponentiate. So we raise e to each side of the equation. So we get e to the negative delta G naught over RT equals e to the natural log of K just equals K. There we go. That's our answer. We just need to plug things into that. Okay, so e to the negative, and remember this is a negative delta G, negative 5.9. This is in kilojoules per mole. R is in joules per mole, so maybe we ought to write this real quick in terms of joules per mole. So times 10 to the third joules per mole. That's the same as kilojoules, 10 to the third joules, divided by 8.314 times 293.15, right? And that's going to equal K. Let's put this in my calculator. I see the exponential of 5.9 E3 divided by 8.314 divided by 293.15. Or you can put the division of the product of R and T in parentheses. Either way. And I get 11.2544. Okay. That seems reasonable. That's saying we have 11 equatorial molecules for every single axial molecule. So equatorial is more common, which makes sense. It's lower energy, but we do see some axial. Okay. And enter our answer to 2 significant figs, which makes sense given what we were told about delta G. Then I get K, or the ratio of equatorial to axial, equals 11.